So you will end up having to create predicted outcomes in a probability metric instead, because people know what probabilities are. And the same thing is true in predicting count outcomes. If you show a plot of predicted log counts, people don't know what to do with that. If you back translate it out of logs into just regular counts, people understand that much more intuitively. So it'll be the same principles in terms of creating predicted outcomes to illustrate what the model is saying, with one extra step of unlinking them back to the original metric. Okay, yeah, I got the second video going here just in case. So every time I start a new lecture, I'll try to stop the recording so that we can keep those separate, hiding this. Anything else before we dive back into linear model stuff?
Yes, Lisa,
Yeah.
I have another question.
Yes.
Can you explain again the relationship between the maximum likelihood estimation and the link functions, please?
The use of maximum likelihood allows us to incorporate link functions, is the way that I would say it. Technically speaking, general linear models use a link function too. It's known as an identity link, which means times 1. So it's not really a change. I would say that maximum likelihood is the machinery that allows us to compute a height given any kind of distribution. The link functions then are a separate but necessary piece that allow a linear model to predict a continuous outcome that nevertheless obeys the boundaries of the original outcome.
Nice. Thank you, Lisa.
Sure.
I just had an aha moment because in R, I used to get an error code that said, like, did you mean to say stat equals identity? And I never knew what that meant. And it was when I was working with general linear models.
Yep. That identity is statistician for times 1. Why? I don't know. Job security would be my guess. How is it already almost 1:30? My goodness. Time flies when you're talking link functions. Doesn't it? That's just to me. But anywho, I've got linear model stuff here, so we are certainly not going to get through all of this today. I have a giant example that I have prepared for this. To give you the backstory of why I'm doing this is I have learned in teaching this kind of material before that people come in with very different kinds of preparation with respect to how you can ask the model for other things that are implied by it than what is directly given. So for instance, what you end up with on your output is, say, the parameter estimates, right? A fixed intercept, fixed slopes. But the model also simultaneously can give you things like differences between slopes, simple slopes as part of interaction terms, predicted values. Analogously, you can ask for any kind of hypothesis test that you want, not just the ones that show up by default on the output. So because I am going to be using those sorts of additional tools in the generalized linear models, I wanted to introduce them, if you haven't seen them before, with just regular general linear models. So this is the purpose of this review. It's to make sure that you and I are on the same page with how I'm going to talk about stuff to come. All right, so it's some review, but maybe some new stuff too. So first off, the general linear model goes by all of these names for particular combinations of predictors and outcomes. When people say the words general linear model, they are almost always talking about estimation via ordinary least squares. So you can fit any of these models using maximum likelihood. And indeed, if you use software like M+, for instance, that's what you're forced to do. So these words have a particular connotation besides just what's in the model with respect to outcomes versus predictors, but also how it's being estimated. One point that I want to make, because this is a common misconception, is that predictors do not have distributional outcomes. So there is all kinds of bad advice out there about cleaning or transforming data, and oftentimes it's presented in a model agnostic kind of way. Like all of your variables have to be normal or else. No, they don't. Even for a general linear model, you can have any kind of x that you want. So the predictors, the explanatory variables, the independent variables, all of those words are synonyms as far as we're concerned. They can be anything they want in these models and in the ones that we're going to cover this semester. So just to review some basics here, the simplest model that you would ever have, for instance, is known as an empty model. This is not something that you may have seen in general linear models because it's not necessary. It is necessary to start with an empty model in a lot of other contexts, and so I want you to have seen it. An empty model has no predictors in it. It is the simplest model you could ever put together. It says that there is one fixed effect. Beta 0 is the fixed intercept for everybody, and E is the individual residual for how far off you are. So for instance, if I have these data here, I'm predicting income in thousands of dollars as my outcome variable, and I want to predict this person's income up here. An empty model would draw a regression line across this predictor that I have not yet included that would be flat. If I don't know anything else about a person, I have no predictors in my model, what is my best guess for their beta 0? The mean, yep, that's the most likely value. So we're going to give everybody a starting point of 17.3 because that's the mean for this outcome. Well, this person makes a lot more money than that, so their residual is positive. And if we take all of the individual E's, so E is this part that's inside the parentheses here, Y for each person minus Y hat, the predicted value by the model, that's the same thing as E that's inside the parentheses. The number we end up with is all of the variance. So this empty model is spitting back to us the mean of the outcome and all of the variance of the outcome as a starting point. Then our job is to refine that prediction. Rather than giving everybody the same predicted value, we give them a custom predicted value based on their predictor variables. So then in this case, I think that one of the things that should be related to income is education. Obviously you guys too, or you wouldn't be here, right? One of the reasons people pursue graduate study is to be able to have additional employment opportunities they wouldn't otherwise have. So if I add education, note that education here is centered. In everything that we're going to do, your predictors shall be centered so that 0 is meaningful. This is not something that often happens in a regression context. It is going to happen because in advanced models, it becomes much more necessary. So I'm just going to start from the get-go by saying all predictors need to be centered so that 0 means something. So rather than having education where 0 means you've never been to school, in this data set, I centered it at 12 years so that my reference person for the model is somebody with a high school degree. So that changes what beta 0 means in this context. It is going to be now the predicted value for somebody with an education of 12 specifically. And it turns out that according to my regression line, where 0 is right here, the predicted value is 14. The slope from these data is estimated at 1.8. So if I wanted to predict for this person up here, who has 8 more years of education than 12, what their outcome is supposed to be, I can use my linear model and get it. So they're predicted to be 28.4. So their prediction is right here, the end of the regression line. But this person is still way higher than predicted, so their residual is still positive. So if we go through this process for every single person in the data set, calculate each person's E, I can get the variance of those E's, and hopefully, if my predictor is useful, I have less variance than I had before. So we started with all of the variance that there is to be had in Y, and we're going down to just what's left over after a predictor in this case. Said differently, we are carving up the variability for this person relative to the mean into 2 parts. The red part is what is explained by education. The blue part is what is still left over. Why does this person make so much more money than anyone else who has 20 years of education? I don't know, but it's for something else. So more generally then, we'll have linear models that look like this, where we have a series of predictors. How the predictors get in is up to you. So most of the time you would have a series of models that are designed to answer specific research questions. That would guide the order and which predictors need to be included. So I'm being sort of agnostic as to that for right now. I want to point out subscripts, less important in this class than in the multi-level classes, but still important. So things that have an I are variables where they vary across individuals in the data set. And things that don't have an I, like the red fixed effects here, all my betas, are constants. So they are the same for everybody. That's why they are called fixed effects, where fixed means the same, as opposed to random, which means different. So the beta 0 term is always the predicted value when all of your x's are 0, which is why x being 0 means something. And each of the slopes tells you the difference in y for a 1 unit difference in x, controlling for all the other predictors. Okay. In terms of what your output would give you for each of these slopes, there's two things that are the most important, because everything else comes from those. So you want to know what is your estimate, what is the best guess for that intercept or that slope from your data. We'll talk about slopes here, and just since that's the ones that we would typically care about significance tests for. And we have a standard error. So the standard error is how far off on average any one sample slope is supposed to be from the population slope. It's an index of how different your slope would be expected to be across repeated samples of the same kind. So even though we only have one sample, we're leaping in terms of inference as if we had more than one sample. And if all of the model assumptions hold, then the standard error is indeed a good approximation of the wiggliness of your results across repeated samples. So if you are making tables for a paper, these two columns are essential. All of the other columns are not. The next column that you would typically see is your test statistic, and it will be either labeled T or Z, depending on whether or not your software is using denominator degrees of freedom. It is the same formula either way, though. It's the estimate minus whatever the null hypothesis is for your test. It's 0 by default, but it doesn't have to be that way, divided by the standard error. So T is nothing but estimate divided by standard error. That's why you don't have to report it. Denominator degrees of freedom, you should already know based on how many predictors are in your model and your sample size. Based on that T value and your degrees of freedom, then you get your P value. In this class, I think all P values will be two-tailed, by the way. Very rare exceptions for things that can't go in both directions, but two-tailed is how we do business. P value, probability of observing a result that extreme or more extreme if the null hypothesis is true. So how unexpected is your result relative to 0, where deviation from 0 is characterized by your standard error. And if you want to, you can take your T critical value that you would use to compare this test against, your standard error and your estimate, and you can plug them into a confidence interval. So all of these things are spit out by your software automatically, but because all of them use estimate and standard error as their ingredients, you don't really need to report all of these things, unless your editor of your journal wants to. So, how are we doing so far? Sounds familiar? Good. Let me see here. We got 5 minutes left. This is where standard error comes from. Just to remind you, it has in it the leftover variance, the scale of the predictor, the slope is 4, and sample size. So standard errors are going to be smaller if you have more people. Standard errors are going to be smaller if you have less variance left over. And standard errors are going to be smaller to the extent that your predictor is less related to other predictors. So ideally, you'd have predictors that were completely uncorrelated. That way, each one gets to do its own thing in terms of predicting the outcome. In practice, that rarely happens. So standard errors can be higher to the extent that your predictors have more in common. And that's just something to keep in mind when you're specifying your models. All right, as I said before, scaling predictors. 0 is going to mean something in everything that we do. When does it matter? It always matters for the intercept. So whether or not 0 is a meaningful value matters for your intercept, because that's what the intercept indicates, the predicted outcome where your predictors are 0. It also matters if you have interaction terms. So we will talk about that in great detail. And as a side note, it also matters in multi-level models when you have random slopes. Because in those models, not only are you going to have a fixed intercept, but you also would have variance around it, random intercept variance that's conditional on 0. So 0's got to be something meaningful within in your data to avoid estimation problems in that latter case. So it's called centering to do this, to subtract a constant so that 0 means something. It's constant centering if you just finished the clustered multi-level course where there was alternatives of group mean centering or cluster mean centering. This is just constant centering. And categorical predictors we're going to spend a little bit of time on Thursday. The process of creating categorical predictors for your categories is called coding. And I greatly prefer a coding scheme that is known as dummy coding, where everything is a 0 or a 1, relative to an effect code, in which the reference point is the mean instead. So one of the things that I will do differently potentially than in other classes is that I am going to ask you to set up your categorical predictors yourself, not to let the program do it for you, so that you have complete control over what they mean. In some generalized models, the option to let the program do it for you is either not possible or way more trouble than it's worth. So I want you to know how to do it. And if you want to take shortcuts in your own life once you know how to do it, that's fine. But I will emphasize this. That way there's a linear model representation that goes directly with your categorical predictors, because it's easy to screw it up otherwise. So that's what we will talk about next time, coding strategies, since it's 143 and all. All right, questions before we adjourn for today?
Really quick, so one of the types of quantitative variables, or we were talking about truncated count variables. So if you center to make 0 a part of that, does that change the classification of the variable?
No. So okay. 0 truncated is usually used to describe an outcome, but you can certainly have a variable that's 0 truncated. In that case, a logical thing to do would be to subtract 1, so that the new 0 is the lowest score you can have.
Okay. Oh, that makes sense, because we're talking about scaling the predictors, not the outcome.
Yep.
Okay.
Yeah, we're talking about what happens to the predictors. And because the intercept is the predicted outcome when your predictors are 0, you want to make sure that 0 is within the range of the scale for the predictors. The grand mean is a very common choice. You don't have to pick that. You could pick a minimum value. You could pick a representative value, just somewhere so that 0 means something that is observed data that you have as a reference. Okay, other questions? Okay, then we will have much more to do on Thursday. Yeah, go ahead.
Quick question. Can you give me an example of your strategy to code? Because in the slide you are saying I prefer dummy coding in which one chosen category reference instead of reference equals overall mean. Can you give me an example of that? For example, with a variable with 3 categories?
I can give you an example of dummy coding schemes on the next slide. Effect coding, I don't have that in here, but I can find an example and show it next time.
Okay, thank you.
Yeah, no problem. I don't like effect coding. I don't find it useful, because I always want my intercept to refer to an actual person, and the mean across groups does not characterize any individual. So I just don't find it as useful. But it's an interpretational preference, not necessarily like right versus wrong. All right, 146 now, so which means we need to say goodbye, sadly. I will let you know where we're going to be on Thursday. I'll just say that, all right? I don't know where we're going to be. I've given up trying to forecast, but at the very least, we will be coming to you live from the basement. So, all right, stay warm. Thanks for coming. See you next time. Bye, everybody.
Bye. Thank you.